All right, in this last chapter or this last section of chapter 4, we're going to be looking at trees and counting techniques. Now, in this chapter, when we talked about probability, right, if we have a list of equally likely outcomes, right, we find the probability of any specific outcome is the number of outcomes that we want divided by the number of outcomes that are possible. Technically, this is called the number of outcomes favorable to that event divided by the number of outcomes in the sample space. Whenever we use this probability formula, it implies that we already know the number of outcomes in the sample space. But here's the thing, what if we don't, right? Well, there's a few techniques that we can use to calculate this. One of them is one of the most important. It's called the fundamental counting principle. And that's if you have a list of specific events, like a series of events, right? And each event has a certain number of outcomes. Then this multiplication rule, this fundamental counting principle, can actually tell us the total number of outcomes that are possible across the entire series of events. So here's the technical definition, right? Consider the series of events E1 through EM, where N1 is the number of possible outcomes of the event E1, N2 is the number of possible outcomes for E2, so on and so forth, and then up to NM, designating the number of possible outcomes for event EM. Then if I take all of those number of possible outcomes and multiply them together, N1 times N2, all the way up to times NM, it gives us the total number of possible outcomes for that series of events from E1 all the way up to EM. Now, it's a complicated definition, but it's and it's a lot easier to explain it using an example. So here's an example. Jacqueline is in a nursing program and required to take a course in psychology and one in physiology, in which they're going to call physiology A and P next semester. And she also wants to take Spanish too. If there are 2 sections of psychology, 2 sections of A and P, and 3 sections of Spanish 2, how many different class schedules can Jacqueline choose from? And we're going to assume that the times of the schedules or the times of those individual classes do not conflict, okay? So if we're trying to figure out the number of possible outcomes that can come from her choosing this class schedule, we have to look at how many outcomes are possible for each choice that she makes. For example, she wants to choose psychology. How many psychology courses, how many sections of psychology are there out there for her to choose? 2, okay? So there are 2 possible sections of psychology. What about A and P? There are 2 sections of A and P. And how many of Spanish 2? There are 3. So, and the way that the fundamental counting principle works is to go through these events one at a time. Okay, she'll choose a psych class, then she'll choose an A and P class, then she'll choose a Spanish 2 class. So with the fundamental counting principle, to tell us the total number of possible outcomes that we take, to find the total number of possible schedules we simply have to multiply all the numbers of every possible set of outcomes. 2 times 2 times 3. So 2 psych classes times 2 A and P classes times 3 Spanish classes. 2 times 2 is 4 times 3 is 12. If you ever looked at a menu for a restaurant, that's also another good example here, where if you are trying to plan out what type of meal you're going to have at a restaurant, where you choose a drink, you choose an appetizer, you choose an entree, and you choose a dessert. Okay, then if you want to find out how many total possible meals you can have, you just multiply the number of all the drinks times the number of all of the appetizers times the number of all of the entrees times the number of all the desserts, and that gives you the total number of possible meals that you have to choose from. Okay. The fundamental counting principle is best visually expressed through what's called a tree diagram. So a tree diagram gives a visual display of the total number of outcomes of an experiment consisting of a series of events. So it basically kind of looks like a sideways tree where you have the root and then you have all the different branches of the tree. So from a tree diagram, we can determine not only the total number of outcomes, but we can also calculate the individual outcomes themselves. So let's use this information to make a tree diagram to show all possible course schedules for Jacqueline. So we go back to the course selection example. Okay. So let's say she chooses these in this exact order: a psychology class, an A&P class, and a Spanish class. So here's my starting point here. There's my start. So let's say she's trying to choose a psychology course first. So this is a psych course. One psych course, or the second psychology section. Okay. Then let's say she goes now to choose an A&P section. So regardless of which one she chooses out of these two, she still has to choose an A&P. A&P 1, actually, let me move these out of the way. A and P. So AP1, AP2, AP1, AP2. Okay. So she chooses a psych course. She chooses an A&P course. Now she chooses a Spanish 2 course. So regardless of which one of these she chooses, there's still 3 Spanish 2 sections to choose from. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And this is what your tree diagram should look like. SP3, SP1, SP2, SP3, SP1, SP2, SP3, SP1, SP2, SP3. So not only can we see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different course selections she can choose from, like we mentioned earlier, but we can also see some individual selections. Like for example, let's say she chooses this psych course with this AP course with this Spanish 2 course. So it's just a visual representation of what a tree diagram looks like. Okay, let's moving on. So here's another example. There are 5 balls in an urn. They are identical except for color. 3 of the balls are red, 2 of them are blue. You are instructed to draw out 1 ball, note its color, and set it aside. Then you are to draw out another ball and note its color. What are the outcomes of the experiment, and what is the probability of each outcome? Okay, so when we we have 3 red balls, 2 red balls out of 5. Okay, so all right, so we'll go ahead and write out this example here using a tree diagram. Use more of the screen so you can see it better. Here is my start. Now, when I pull a ball out of the urn, there's one of 2 choices. Either it's going to be red or it's going to be blue. So either it will be red and it will be blue. Now remember, there were 3 red and 2 blue out of the total 5. So your probability for choosing the red would be 3 out of 5, which would be 0.6. To choose the blue, the probability would be 2 out of 5, or 0.4. Actually, leave those parentheses off here. Okay, that's the color of the first ball. Now when I go to draw a second ball, again, when I go to draw the second ball, I have one of two choices. Either it's going to be red or it's going to be blue. Same thing the other direction. No matter what ball I choose the first time, the second one's either going to be red or blue. But what are the probability of those happening? What's the probability of those happening? So this is where conditional probability comes into play. So after I choose the first ball, there are now 4 balls left to choose from. 2 of them are red and 2 of them are blue. In this case. So the probability that I choose another red is 2 out of 4, or 1/2. Now, if I choose a blue, I have the same probability. Well, no, I have different probability actually before, because we're not replacing the ball, and these are not independent events. Yeah, that probability is also 0.5. Now, when I go to choose the blue ball the first time, then I will, so when I choose a blue ball the first time, there are 4 balls left. 3 of them are red. 1 of them is now blue. So the probability that I choose a red is now 3 out of 4, or 0.75. When I go to choose another blue, that's 1 out of 4. So that's 0.25. All right, let's go ahead and look at these different probabilities and see what they end up being. Okay, so there are 4. Now, if I were only to choose 2 colored balls out of the urn, that makes up 4 different possible outcomes. Probability that I choose 2 reds, probability that I choose a red and a blue, probability that I choose a blue and a red, and the probability that I choose 2 blues. And the multiplication, this is an AND probability, so the multiplication rule does apply. And the good thing about this is using a tree diagram is we're already calculating the given probability. Whether or not these events are independent or not, we can still use a simplified multiplication rule for that. So, for example, when I want the probability of 2 reds, well, the first one being red is 0.6. The second one being red after the first one's red is 0.5. So 0.6 times 0.5, that's 0.3. Now the probability that I choose a red and a blue, it's the same probability because both of these have the same probability here, 0.3. Now, what about the probability that I choose a blue first and then a red? Because so then I would take that 0.4 times 0.75, and I would get 0.3. And then our last one, the probability that I choose 2 blue ones, that's 0.4 times 0.25, that being 0.1. And if I take the sum of all these probabilities, 0.3 and 0.3, that's 0.6, that's 0.9, I get 1. As it should be, because it's the sum of all the probabilities. So, moral of the story is, a tree diagram is really good with, especially with using AND probabilities, right? It's good at being able to identify not just the sample space, but also the individual probabilities and individual outcomes that we might want to look, not just in the broader spectrum, but even on the more specific spectrum. Okay, so let's go on to the next thing. Sorry, just did that one. Okay. Now, sometimes when we consider a certain amount of items, sometimes we might want to know how many different ways we can arrange them. A good tool or a good function that helps us to navigate this is called the factorial function. Not because not every arrangement of items is equal to the number of items being arranged. So for specific applications, factorials are needed for things like permutations and combinations, right? So we'll get to those in a second, but just in general, we'll start with factorials to get us into learning how to arrange a certain number of possible items here. So what's a factorial? So the factorial of a whole number, and the way it's written as, so the factorial of a whole number, we call this n factorial. So it's the product of every number less than or equal to that whole number. So for example, if I wanted to figure out what 5 factorial is. So here's 5 factorial. That's what the exclamation point means. 5 factorial is 5 times 4 times 3 times 2 times 1. Now, for any whole number, including 0, you don't do negative numbers for factorials. The way that we calculate factorials, 0 factorial and 1 factorial are both the same. They're both equal to 1. But 2 and above, you take that number multiplied by every number less than or equal to it until we get to 1. So back in the previous example, 5 factorial was 5 times 4 times 3 times 2 times 1. Okay. For example, if we're going to evaluate 4 factorial, that's 4 times 3 times 2 times 1, right? You can either do that all in your calculator, or you can take them one product at a time. So 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is 24. So 4 factorial is 21. So we use factorials to determine how many different ways in which 8 people can be seated at a dinner table, right? And this comes from, you can use a factor tree to figure this out. So like, for example, or you can just, kind of draw it out, right? So if we have 1, 2, 3, 4, 5, 6, 7, 8 people to choose from, or 8 people that we're seating in 8 spots, right? When I choose the first person, I have 8 total people that I can choose from. When I sit that person, then I have 7 people left to choose from. When I sit that person, I have 6 people to choose from, and so on and so forth, up until I seat the last person. And that's why the factorial is so important, is because factorials can really help us out in finding different ways to arrange a certain number of people around in a certain space. Okay, so for factorial, if you're using a graphing calculator, I'll show you how to find factorial. So if you press the math button here, and you scroll all the way to the right where it says probability, there are 3 different options that we're going to use in this section. The first 2, NPR and NCR, we're going to talk about a little bit later. The 4th one is your factorial option. So you can calculate yourself, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Or I can press 8, go to the math section, scroll to the probability section, choose option 4, 8 factorial, which gives me 40,320. But what if we didn't arrange the entire group? Because we do run into situations where we're trying to arrange a certain group of people, but we're not using everybody in that group. So the question is, let's say that we're doing the same thing. We're having a dinner or having an open house, and we have 8 people in this open house, but we only have 5 chairs. How many different ways can we arrange 5 of those 8 people? So again, as I mentioned earlier, not every arrangement of items is equal to the number of items being arranged. We need specific applications of the factorial called permutations and combinations. For this particular example, if we're arranging 8 people 5 at a time, right? If we're finding ways to arrange 5 out of those 8 people into these chairs, we use a permutation. And here's the permutation. So a permutation is a number of ways to arrange in order of n distinct objects, taking them r at a time. So there are a couple ways that you see this notation here, p with a subscript of n, comma r, or in the calculator you see in PR, like this. I usually like to use this notation because it's easier to write and it's also easier to type. But the way that we calculate that is we take n factorial divided by n minus r factorial. Again, n and r are whole numbers. Okay. So when we are calculating this example, compute the number of possible ordered seating arrangements for 8 people in 5 chairs. When you do a permutation, and eventually we'll get to a combination, the larger number always goes here on the left, regardless of whether or not the number of arrangements and the number of things that you're arranging are the same. It always goes on the left side. So if we're taking 8 people and we're arranging them 5 at a time, then that formula becomes 8p5. Okay? I'm going to show you how to do it by hand, and I'm going to show you how to do it using a calculator. So to do it by hand, use the formula, right? NPR equals n factorial over n minus r factorial. Okay, so that's 8 factorial divided by 8 minus 5 factorial. Now if I simplify this, this becomes 8 factorial over 3 factorial. Now if I were doing this by hand, a quick way and a great way to simplify this is to write out the numerator first. 8 times 7 times 6 times 5 times 4 times 3. Now I'm going to stop there and put the factorial symbol here. Now why didn't I go 3 times 2 times 1? Well, by definition, 3 times 2 times 1 is 3 factorial. Why is that important? Well, look what's in the denominator. 3 factorial, which means that this and this will cancel out, and I don't have as much to multiply. I have 8 times 7 times 6 times 5 times 4. So if I calculate that, 8 times 7 times 6 times 5 times 4, I get 6,720. Okay. Now, to do this in your calculator, all right? So when we go back to the math section, the same place we found the factorial, the permutation button is number 2, NPR. Now when I click that, I need to put a number in front and a number behind. So when I put this in my calculator, it's going to look like this, 8 NPR 5. So what I'm going to do is I'm going to press the 8 button first. Then I'm going to press my NPR button down here. Then I'm going to press 5. And then I'll press enter. And I get the exact same thing. Now what happens if N and R are the same? Well, I believe I've actually written that in the notes. Yes, I did. So even though it's not shown up here, I'll write it down on here. If N and R are the same, if N is equal to R, then that permutation NPR, right, or NPN, whatever, it's just the factorial. right? Let's go back to the example we were seating of having 8 chairs instead of 5, right? 8 people, 8 chairs. Those two things are the same number. I calculate it using 8 factorial. But when it comes to 8 people, 5 chairs, that's where I have to use a specific permutation. Okay. So if n and r are the same, then I use n factorial. But if n and r are not the same, keep in mind the larger number goes to the left, then I use a permutation. Okay. Now, here's an example. Calculate 12p7 in your calculator. Again, actually, I don't need to write this down. Again, 12, press the math button, scroll all the way to the probability section, press option 2, and then 7. And I get 3,991,680. Okay, now we'll get into talking about combinations. A combination of n objects taken r at a time. It's using the same notation as permutations, right? NCR or C n comma R, right? It's using the same style of arrangements except for one difference. Okay. With permutations, you're arranging those objects in a specific way, so the order does matter. But when it comes to combinations, the order does not matter. In other words, for example, let's suppose that in your English class you're given a list of 10 books. You are to select 4 books to read during the summer. Does it matter what order you read those books in? No, just as long as you read the books, right? It's like saying this. I'm going to use an example. Let's say I take 3 people in this class. Let's say I take 3 people in this class and I send them out to the library to get something for me. Does it matter what order they go out in? It doesn't. I would use a combination. But when it comes to permutations, when the order does matter, that's like saying I'm sending one person to go do this in the library, another person to go do this in the cafeteria, and a third person to go do this in the office, right? So the order does matter more for permutations than it is for combinations. So the formula for combinations is also similar to the formula for permutations, except this, right? So this part here comes from the permutations formula. But what's with that r factorial? What's with that r factorial? Well, what the r factorial is, it's the number of ways to arrange items in the same group, right? So for example, using the example that I use in class, if I'm sending 3 people to go out if I send 3 people to go out to do specific things for me, one person to go to the library, one person to go to the cafeteria, another person to go to the office. So the order that I choose them does matter, right? I would use 3 factorial. So 3 factorial, that would be 6, right? And that, of course, that would be a permutation, 3p3. But when it comes to combinations, and let's say I choose those 3 people to go to the library to get something for me, the order doesn't matter in which I choose them. Those 6 combinations are reduced to 1 because the order that I choose them does not matter. Okay, so before we do some examples with combinations, a real quick thing. So remember I said if n and r are the same for permutations, you just use the factorial. For combinations, if n and r are the same for combinations, then that combination is just 1. Okay. However, if n and r are not the same, then you use this formula here. Okay. So let's look at an example. Suppose that in your English class, you are assigned to read any 4 books from a list of 10 books. How many different groups of 4 are available from the list of 10? Okay, order doesn't matter. So we need to use a combination, right? Larger number always goes to the left. 10C4. Okay? If I use the formula, remember it's n factorial over r factorial times n minus r factorial. So that's 10 factorial divided by 4 factorial times n minus r, 10 minus 4, 5 factorial. No, sorry, that should be a 6, not a 5. 6 factorial. Okay? And again, I'll show you how to do this by hand and in the calculator. If you're double checking your work, when you do combinations, the two numbers that make up your factorials should add up to the number in the factorial at the top. Okay. So again, if you're doing this by hand, let's rewrite the numerator. 10 times 9 times 8 times 7 times 6. Notice that I have a 6 factorial here. So what that's going to do is it's going to cancel out the 6 factorial in the numerator and the denominator. Now I'm also going to expand this. So 10 times 9 times 8 times 7 times 4 times 3 times 2 times 1. Now why am I doing this? I'm doing this so I can keep reducing this fraction a little bit more, right? So for example, I know that this 4 and this 8 share a common factor of 4, so this reduces to a 1. 8 divided by 4 is 2. Same thing here. This reduces to a 1. This reduces to a 5, right? So, and then of course 3 and 9 have a common factor of 3. And so now I've completely gotten rid of the entire denominator because the denominator is just going to be 1 now. So that's 5 times 3 times 2 times 7, a much easier number to calculate. That's what, 15 times 14, right? Which is, let's see, 140 plus 70. That's, I think it's 210. There's my combinations. Okay. Let's use the calculator, right? Same process. 10, press the math button, scroll all the way to your probability button, and this time NCR is option 3. And my other number is 4, and I get 210. Now, let's suppose that the order does matter. Well, instead of a combination, we would use a permutation. And when I use a permutation, I get a much larger number, 5,040. Right? That means there are roughly about 4,830 different arrangements that involve the same groups. Okay. Now, to recap, if you have an experiment, if you're trying to determine the number of total outcomes in an experiment, what you want to do is first look at the experiment itself. If it consists of a series of stages with various outcomes, if it's a series of multiple events, each of them having different outcomes, you use the fundamental counting principle or you use a tree diagram, okay? But if your experiment and your outcomes consist of arranging items, right, in an particular order, then you use permutations. Now, if you're taking arrangements of objects where the order doesn't matter, then you use a combination.